Let me share my screen.
While Lars does that, make sure to go over the outline and start working on the weekly project, the weekly homework, and the project.
Okay. So today is a continuation of last week's lecture about optics. So last week we introduced two optics, lenses and traversals. So a lens focuses on precisely one substructure, like the field of a record. That's always there, and we know there's exactly one. And traversals focus on several fields of the same type. So for example, we had the each traversal for traversables, which focuses on every element in a list. And today we will get to know two more optics, so-called prisms and ISOs. We actually have seen ISO already last week when I had this example. I think I called it lazy. That basically is a lens from a strict byte string to a lazy byte string. And that's, we already said that's a bit strange because, I mean, with a field of a record, the field has strictly less information than the record itself. It's just one field. But with this lazy and strict byte string, it's exactly the same information. It's just in a different format. So we will make that more precise this time. And the plan for the lecture is to first talk about pro-functors, which we will need to define prisms and ISOs, but a priori have nothing to do with lenses. And they are quite a useful type class in Haskell, although it's not as important as the ones we have talked about before, like functor or foldable, traversable, applicative, and monad, for example. Then we'll talk about prisms, then ISOs, and finally, that is then a very small step, actually, polymorphic updates. So let's start with pro-functors. And before I do that, let's not talk about pro-functors. Let me just start a REPL. And if I ask about information on the function arrow, so the just functions from A to B, then we see that in particular, it has a functor instance. And I think we haven't talked about that before, how that is a functor. So, I mean, I can't write this instance now because, I mean, it's already defined in the prelude or in base, but I can try particular to get the fmap. What would be fmap in this case? So given a function from A to B, and actually I should write it, let me write it this time different. Let me write it as B to B prime. The function from A to B, we need a function from A to B prime. And maybe make it more explicit that we are talking about this arrow by writing, sorry, great. Writing this a little bit different. I write this with this explicit form of writing functions that I also mentioned before. So that's okay. Okay, and I don't know, FG. Now it will complain. Right. It's must give it one argument because a functor always has kind star to star, and the function arrow has kind star to star to star. So I must fix one argument. So the first, the domain. Now it complains, I suppose, that, yeah, it's already defined in base. I could maybe get that. I could give this no implicit present prelude, but I just comment and now it doesn't matter. Right. So, I mean, we have a function from A to B, So this is now this functor or this type constructor functions starting in A with domain A to somewhere. So I have something from A to B, and now as usual with fmap, I have something from B to B prime, and I must turn this function from A to B into a function from A to B prime. So I mean, we have this G, which goes from A to B, and we have our F, which goes from B to B prime. And in order to implement fmap, I need something from A to B prime. And that's, of course, like obvious what I need to do. I mean, I just compose F and G. So the implementation would just be F dot G. And that's actually the functor instance given in the base libraries. So far, so good. Actually, we see it's also applicative and monad. And maybe we can, I think we will talk about that in the next lecture when we talk about monad transformers. But this is not the focus of today's lecture, how this functor is actually even a monad. Okay, so far so good. So functions where basically we keep the domain fixed, the A fixed, are a functor, because I have this implementation of fmap, which is just given by the usual dot, the usual function composition. You must just convince yourself that this is indeed the signature of fmap in this case. So in a sense, functions or the functions from A are some sort of like the mother of all functors. So it's like a special functor in some sense, or the most like general functor. But anyway, right, so far so good. But I mean, if you look at this diagram, so we have this function G, and I mean, if you have something from B to B prime, we can compose with it and get a function from A to B prime. However, I mean, we could also, I mean, you can compose here, but obviously you can also compose on the other side. So let's say we have something from A prime to A. Some, I don't know, H. Then we could also compose our original function with basically on the other side. So it's fg, but if we have this h, we could also do g dot h on the other side. But that is not captured by this functor instance, right? We only talk about composing on this side. That's how functor works. But nevertheless, I mean, there's more structure to the function error, because if we did something on this other side, we could also compose. But functor doesn't capture that. I mean, functor only has one argument. So in this case, the B is basically the argument. And if we have something from B to B prime, we get something value of the functor applied to B, functor applied to B prime, fmap. But I mean, arrows are actually, they have two type arguments. So we could only turn it into a functor by fixing one argument here. And the same is true for either, for example. I mean, we know either A is also a functor, and the B is basically then, if we have something from B to B prime, we can turn it into a functor by defining fmap from either AB to either AB prime. But the A is always fixed. Right. And now the idea of pro-functors is now to not only consider one type argument, but type constructors with two arguments where both arguments can vary, like arrows. So there is this something called, sorry, it's a class. It's called pro-functor. And it takes some type constructor now of two arguments. And instead of just map, we have something called die-map, given something from A prime to A, and something from B to B prime, and sorry, and something in this functor applied to AB, we get something in F A prime B prime. So we can, I mean, fmap only wiggles on one side. So fmap would be basically die map where this is the identity. So we only operate on the second argument. But now the difference for pro functor is that we also do something on the first argument. And also note that the direction is different. So in order to go from FAB to FA prime B prime, with die map, we have something from B to B prime. So from B to B prime, but this A prime to A goes in the other direction. And you can also see this here with function composition. So yeah, so basically composing on the left reverses the, I mean, we have something from A prime to A, but by composing with G, we have something from A to B and go to A prime to B. I mean, for the technical term for that is contravariant. So it's covariant in the second argument, but contravariant in the first. Anyway, and this diagram shows that we have an instance, like the canonical instance of profunctor is just a function error, which is explained by the diagram already. So if I have f, no, what should I call it? I mean, to be in sync with this diagram, I would have to call it HFG. And it's just G composed, sorry, F composed with G composed with H. Right. I mean, this is how function composition works. So function has two arguments, the domain or the domain and the codomain. And if you change the codomain by giving something from B to B prime, and if you change the domain by giving something from A to A prime to A, then you get a new function from A prime to B prime simply by composing. So it's nothing more than just usual function composition. Okay, but the idea of profunctor is now that we can generalize this. So it's not just function errors, but we may have other things that behave like this. Are there any questions at this point?
Nope.
Okay. So let's look at two more examples of profunctors to show that it's not just functions. Just clean up a bit. Right. If we look at monads, I mean, a monad is only of kind star to star. So we have monad applied to one argument. So it's basically effectful computations with effectual computations that with a result type. There is, however, a way to basically look at monads with two arguments, and that's the so-called Kleisli category. I think that's the name of a mathematician. So let me just write the definition. Right. I mean, this doesn't say anything about M, A, and B, but the idea, of course, is, I mean, as the name suggests, that M will be a monad. And the point is that we will have a profunctor instance, profunctor Kleisli M, provided that M is a monad. Why is it complaining?
I think you imported without wanted to.
Yeah, I probably did. Oh, yes. That's right. Okay, so obviously we must implement die map. So this is now A to A prime and B to B prime. That's the same for each cofunctor. But now we have Kleisli MAB to Kleisli MA prime B prime. Okay, let's call it H and F again. Right, and let's first look at this. So try to draw a picture. So we have our Kleisli MAB is by definition of Kleisli. I mean, if I forget about the new type constructor for a second, I mean, this is just needed for technical reasons, but it's easier to see what's going on if I don't have that. So I have my A to MB. That's the thing I start with. And what I need in the end, here at the end of this die map, is something from A prime to MB prime, right? And now I have given this H and the F. So the H goes from A prime to A. And my B is from B to B prime. Okay, so those three things are given. The Kleisli MAB, again, I dropped the new type constructor now to make it clearer. So basically an arrow from A to MB, just a function from A to MB. Then I have my H from A prime to A and my F from B to B prime. And what I need in order to implement die map is A prime to MB prime. So the H part is easy, right? I can just compose this given thing with the H. So I have something from A prime to MB. So now how do I get from MB to MB prime? But that's also easy because I have something from B to B prime and M is a monad. So in particular, M is a functor. So I can just F map. So I have F map F from MB to MB prime. Okay. And that's how I'll implement this. So I don't know how to call it. K for Kleisli maybe. So what's that? So it's Kleisli. So now I need the new type constructors. So now what's this? That's F map F composed with K. So that's, I must unwrap the Kleisli to get to this function. So run Kleisli K and then composed with my H. I think who is complaining? Oh, yeah. Right. And this is, and now it's still something wrong, I think. Did I make a mistake?
I don't see it yet. Why is H also an error at the end?
Yeah, it claims it has the wrong type. Oh, yeah. This is. right?
Oh.
I mean, I copied it wrong from the definition. So it must be, I mean, that's the whole point. It's the other way around. Okay. So that's one example. I mean, another example, the function error is the canonical example, but this is another example. And just by the way, I think that's not in the slides, but I just want to show one other thing because we need it later, or not really, but it's remember last time I had this control category, which also has definitions for identity and composition. And we used it as an intermediate step when we had our naive lenses just with getter and setter, and then we wanted to compose them. I made them instance of category so that we can use the dot and it, not just for functions, but also for other stuff. And then later I deleted that again because we didn't need it anymore because our lenses in the end were just normal functions. But I just nevertheless now want to show that this Kleisli thing is actually also a category, and it's also a nice like repetition of what category is. So I claim that Kleisli is actually a category. So that means, why is it complaining? Oh yeah, Kleisli M. I mean, Kleisli has 3. Actually, if it's a monad, so monad category Kleisli. So we need identity goes from, so it's in Kleisli MAA. And we need composition, Kleisli MBC, Kleisli MAB, Kleisli MAC. Right. So it's maybe a nice exercise to, it would also be a good homework exercise. But nevertheless, let's just do this. So we need something, I mean, for identity, so Kleisli MAA. So basically we need something from, by definition of Kleisli, if we again forget about the U-type constructor, we need something of type A to MA. And that, of course, screams pure or return because M is a monad. So we must just wrap it in the Kleisli constructor. So it's just Kleisli pure. And for this, so what's the picture? So this Kleisli MBC is something from B to MC. And this Kleisli MAB is something from A to MB. And now we need something from A to MC. This is what that said. And I mean, this is obviously just monadic bind. So we can do this. So we have Kleisli. And now I can, for example, use do notation. So starting with an A, just to get this MB here, I need the first arrow. So run Kleisli L applied to A. This is now an MB. And now I just bind to this, getting a B. And then I can apply the second one. So run Kleisli KB. So I could write that shorter as run Kleisli LA run Kleisli K. And this, right, and now I already get the hint because that has actually a name in the standard libraries. So if we have a monad M, so it's called this. So if we have a monad M, something from A to, okay, let me use the same names for the type, something from A to MC, B to MC, and A to MB. I get something from A to MC. And this is basically the same I did there. So KL is just a Kleisli LA Kleisli K. Let me just disable that hint.
It's imported by Prelude.
Yeah, but why is it 17?
You might need to hide it, or
Yeah, but why? I mean, Prelude is fine. More optics 50. Oh, yeah, right. Okay. What now? Oh, yeah, it's the wrong way around, I think. No. Yeah. Sorry, this is not, this has the other way around. I think A to MB, B to MC, A to MC. Okay. Oh yeah, there is no run Kleisli, of course. Sorry. I mean, this doesn't say anything about Kleisli here. There's no, sorry about that. Right, it's easier because I don't have this Kleisli constructor. Anyway, so this is a definition of the standard, and then the point is that I can then use this and instead write this as run Kleisli L run Kleisli K. Right. This is incidentally, I mean, this is just, it's not important, but somehow it's nice. I mean, if you have ever wondered, I mean, the definition of the bind in monad is somehow asymmetric. I mean, it has this A to MB. I mean, if you have MA and then A to MB gives you an MB. But that's somehow, and then especially if you express the monad laws using bind and pure or bind and return, it's somewhat ugly. I mean, intuitively, it means something like associativity, and that return is like a left inverse or right inverse for bind. But that is actually a bit ugly. But interestingly, the monad laws are equivalent to return so the point is basically a monad and a so-called Kleisli category are more or less equivalent. And if you write it in this form, it's sort of more symmetric or nicer. And in particular, the monad laws are much nicer. So in the so-called Kleisli category, The monad laws really just point down to that return is a neutral element with regard to this composition, and that it's associative. I mean, that's not important. I mean, especially for mathematicians, it's somehow pleasing because these monad laws, if you first look at them, they look very ad hoc. I mean, somehow complicated, and one wonders why one would come up with these laws. If you rewrite it in this form, in this Kleist-Leaf form, then it's much more symmetric and obvious why you would want these properties. Right, but that's actually just an aside. We don't need Kleist-Leaf today for the optics. It's just another example for profunctor. But there's a final example for profunctor that we do actually need. And for that, we introduce a new type tag. And remember last time const was quite important. So we had this const AB, which just contains values of type A, and the B doesn't matter. And tag AB is very similar, except now it just contains values of type B, and A doesn't matter. And we consider it as a functor in a profunctor where both A and B can vary. So the definition is just, so it just is a B. And the point is that we can turn it into a profunctor. So it's basically, it has a similar importance for profunctors as const has for functors. So we can give it a profunctor instance. We need this die map. So A prime to A, B to B prime, tag AB, tag A prime B prime, die map. What did I call it? HFK or HF something. Right. So we have something, this tag, which is just a B, and we need to produce something which just has a B prime. So that means we can completely ignore this first function because there's no A anywhere inside. Don't even have to give it a name. We can just apply this F, the function B to B prime, to the tagged value in here, to the B. So to do this, we have our T, we untag it. Now we get a B, and we can apply F to it. Now we have a B prime, and we can apply the tag constructor again. It's called die map, phi map. Right. So that's that. Let me just check on the slides. So the first couple of slides, you can ignore them. They assume that you know about category theory, which you don't, but it's basically just an explanation of profunctor again. So in particular, this thing here, that if you have something profunctor of x, y, then you can compose basically on both sides. But never mind. So here are the examples. In particular, function arrow, Kleist-Leaf category, and tagged. Oh, it's called tagged. I thought it was tag. Sorry. Right, and untagged. Okay. Okay. So here are also basically diagrams explaining how you can get this die map. And there's one more type class we need for the optics. And again, it's maybe a useful one, but it's not very common. So don't worry too much if you don't remember it. I mean, I've never needed it from like my Haskell, my personal Haskell projects, except for its use with optics. So that's called choice. So let me just also type that. So if we have a profunctor, profunctor P, then we define a new class which is called choice. And that has left prime. So given a PAB, we get something in the same profunctor, either AC, either BC. And symmetrically, right does the same on the other side. So either CA, either CB. Right, and actually you only need to implement one of the two, because so you can define right prime in terms of left prime and left prime in terms of right prime. And so that's that. I'm not sure whether we should show how. Also forget how this minimal works. Never know the syntax, is it? Just a second.
In this case, I think just minimal and the or the
Yeah.
I
Is
think that
it minimal?
yes.
Right. There should be actually, if I look at the source here, that should be
Yes,
there.
it should be there. Yeah.
I have tried here. Yeah, like this. Great. Okay. Why does it complain about that? Or because I need to implement defaults if I claim this.
Yes.
Okay, so how can we define this in terms of right? So we have we have a PAB, and we need something this shape. But if we want to define it in terms of right prime, then basically all we can do is we apply right prime to this. But now we have the wrong shape. We have a P either CA, either CB, but we want P either AC, either BC. So with the two swapped. And this is actually a nice exercise for things, what we said right in the beginning, that if you have a very polymorphic function, normally it's easy to implement because you don't know anything. We don't know anything about P, A, or B. So all we can work with, all we have is that, now we have this right prime and that P is a profunctor. So the only thing we can possibly do is apply dymap. So dymap __. So that's the plan. And now the compiler can basically help us. So in order to get this first, let me just comment this for a second because it's complaining now until I've done these default things. Right. So we need something from either AC to either CA. And right, I think I have talked about either small, but maybe just a second. Let me just remind you. So there is something called either. I have something from A to X, from B to X. Then I have something from either A, B to X. Let me just So that's defined. Let me just define it again to tell you how that works. So that's basically the catamorphism for either. So I mean, if you wanted to do something like this by hand, so we have something, let's call it AX and BX and an either. So what would we normally do? Well, we would pattern match on the either. So the either can either be a left A, in which case I just apply AX to it, or it can be a right B, in which case I can apply BX to the B.
Lars, there are a question?
Yes,
No.
just 1 second. Okay, yeah.
Said,
the-
could you please explain again on using the pragma minimal?
Yeah, I'll come to that. Right.
Maybe after the definitions.
Yes. I'll come to that. At the moment, I'm not using it anyway. Right. So this is this either. So I called it either prime because otherwise it will complain that. I mean, I can also call it either, and then I just have to hide it. Right. So this is so either to get, so basically what either does is to give something out of an either to X. I need a function from A to X and from B to X. And once I have that, I could define it like this. So it's a compact way to write something from an either. So then I can use that here. So I need something from either AC to either CA. And I want to use either. So let me do it slowly. So I want to use either. So I want to use either here as well. Basically, I just don't even have to think about it because now the compiler tells me everything. So here I need something from A to either something A. And the only choice I have there is to use right. Here I need something from C to, so the only choice I have is left. Here can only do right. Here I can only do left. But what that does is it just swaps around. I mean, I need to go from either CA to either AC or the other way around. No, actually this way. No, from here to here, either AC to CA. So I just have to swap the two arguments. And that's exactly what either right left does. And right. Okay, so that's that. And now I can do the same here. So I can define right in terms of left. Again, die map. Again, the same trick. So probably I should have given this a name because it appears 4 times. Right, so so the point is I can define left in terms of right and right in terms of left. That means if I want to instantiate this class, I don't need to define both. It's enough to define left or right. And that is where this minimal pragma comes in to answer the question. Why is it still complaining? I think it must be on the,
Maybe must,
yeah. Oh, yeah, must be indented. Right. So that just tells basically not even the compiler that it's enough to implement left or right, that I don't need both. And basically, if I implement left, then right will just use the standard definition here. And if I just implement right, then left will use the standard definition. Okay, I hope that answers the question. And I mean, this is very abstract. And I mean, why it's called choice, who knows? But I mean, we will see what it's good for later. But I think it's nevertheless useful. I mean, in Haskell, sometimes the types get so complicated that it's difficult to intuitively understand what they actually mean, if they mean anything. But sometimes it doesn't matter. I mean, you can just let the compiler help you, guide you to implement stuff, even if you don't really intuitively understand what's going on. And I think that's also an important skill that you have to learn when you do Haskell. Right, and now the point, of course, is that all our 3 examples will actually be instances of of choice. So let's write them. So I claim that that our function error is an instance of choice. And now, right, and now see, I get this warning here. No explicit implementation for either left or right. If I had deleted this, if I hadn't the minimal practicum, then it would say, no, then it doesn't say anything. Oh yeah, because I have like default implementation. So then I think I don't write, but now I get the right error message or warning. So let's do left. So in this case, P is our function error. So I have a function from A to B. And I need a function from either AC to either BC. Okay. So given this function, I need something from either AC to either BC. And that's again something I can do with either. So then I need something from do something wrong. That's strange. I don't know, it's not strange. Right. So I need something from A to either BC. So given an A, so I must either produce a B or a C. There's no C anywhere inside, so no chance to get a C, but I can get a B because I have this function AB going from A to B. So I can apply the function AB to my given A to get a B and then use the left constructor. Right, so I can do left after AB. And here I need something from C to either BC. So no chance to get a B, but I do have a C, so I can just use the right constructor. Okay, and now it probably complains about brackets, but I did that on, yeah, that's indeed stupid. No, I should have red brackets here. That's what I intended. To make it clearer that the profunctor is the arrow now. Okay, so for this, it's easy. Now let's look at Kleisli. So instance choice Kleisli M. And we do need monad, or at least functor, I think, anyway. Okay, let's try left again. So what's it in this case? So again, given something from, so now we have Kleisli arrows. So we have Kleisli MAB, and we need to go to Kleisli M either AC, either BC. Okay, let's draw a picture again. So we have this Kleisli MB. So that's something from A to MB. And what do we need? We need something from either AC to either to M, either BC. Right. I mean, it's not immediately obvious how to do that, but let's do it step by step. So first we need to get to this arrow. So that's just by run Kleisli K. So now we have this arrow available. Okay, and now what? Or rather, sorry. I mean, we need something like this, but it must be wrapped in a Kleisli constructor. Okay, and it's something that starts in either, so we can use the small lowercase either again to actually define this. Okay, so now what do we need? This tells us we need something from A to M of either BC. So let me write that. we need. So we need something from A to we need either B, C. Right. And then also we need something from C. M of either B, C, which will be easier. Okay, but here similar to what we did for choice instance of error. So we have something from A to MB. So I can apply this function here to my A. So I have something of type MB, but I need something of type M either BC. So if it was just from B to BC, I could do the same I did here, namely left. But instead, I need something from MB to M either BC. So I just use the fact that M is a monad and hence a functor. So I do fmap. So it's very similar to the instance for errors. Instead, I can't just compose. So again here, so instead of this AB, I now have run Kleisli K. And I can't just use left, I must use fmap left. 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 Okay. So that's this part. And the other one, I think that's easy. Right, because I can get from C to either BC using right, and then I can just use pure. So that's just pure right. So I mean, here I do the intermediate step, either BC and then to this. So for the first step here, I use right. And for this step, I use pure. Okay, but again, we don't need Kleisli for the optics. So it's just basically another example how one would write such an instance. We will, however, need it for tagged. So let's do tagged. So the last example here of profunctors. So instance tagged, choice tagged. Okay, again, let's try left prime. So tagged AB to tagged either AC, either BC. Okay, so tagged is basically just a B wrapped in a new type constructor. So I have a B that's here. So now what I need is an either BC, also just wrapped in a new type constructor. So it's tagged. So now I have my T, so I can untag the T to get a B, but now I need an either BC, so I can just apply left to it. Right. Okay, so that's the choice instance for tagged. So we now have, and I mean, I know this is all very abstract. I'm sorry for that, but yeah, it's also part of Haskell to sometimes have these weird type classes that one doesn't really understand what they're good for. But nevertheless, it's possible to writing diagrams and letting the compiler help you to actually implement stuff for this. Okay, but now we will, so that's that. So we must just keep that in mind, these profunctors, because we will need them later to implement our optics. But now we will first get much more concrete. We just, I think I just renamed this to profunctor or something that we can use it then. Just so profunctor. And what did we have? Choice. And Kleisli, we don't even need this, but also doesn't do any harm. And tagged.
We have a question from Tony. Is left some time of function? I remember it's a constructor.
Yes, and constructors are, of course, functions. I mean, if we ask for definition of either has two constructors, and left, it can be a left A or right B. And of course, constructors are special cases of functions that construct a value of a data type. So left takes an A and gives us an either A, B, and right takes a B and gives us an either A, B.
Thanks. Yeah.
Okay. Right, I just wanted to, I think instead of more optics, let me just copy this and call it profunctor. I mean, we didn't need to define that. That's of course in some library, but nevertheless, let me just profunctor. And let me delete everything here. See? Other questions?
No.
Okay.
ISDS.
Oh, right. Okay, this seems to be okay now. Right, so that's profunctors. So choice. Okay, so maybe I can at least, like, we can introduce prisms. Ah, yeah, there's one other topic before, and then we can have our first break. Okay, but just to remind everyone of the last lecture, so we had two optics, lenses and traversals. And the lens SA was something where basically that zooms in from an S to an A. So the A is in some sense a part of the S, and we can basically, given the S, we can reach into it to grab this A. And then we had traversals, also same type parameters, an S and A. And the difference is that it can basically zoom in to arbitrarily many A's that are in some sense contained in the S. And I mean, first we had this naive or concrete definition for lenses with just a getter and a setter. And then we saw if we write it in this weird form as a special function, then we can give both lenses and traversals the same shape, similar, I mean, function of a similar shape. And the cool thing about that was that then composition of lenses and traversals is just usual function composition. And we can even compose lenses with traversals, so we can freely mix them. So a lens composed with a lens is again a lens, and everything else composed with each other is a traversal. And we can set and view the parts in focus. We can list them with toListOff, and we can apply function to them via over. And we also have effectful updates, so what we call overF. But we don't even need a special name for that, because that's just baked into the very definition. So the way we ended up writing our lenses and traversals is just this overF. Right, so that's where we were last time. And if we look, let me just go back to optics. So I basically copied the code from last time. And if I look for toListOff, then we had this definition. So in principle, I think we started with a traversal or something. So we had this traversal here. Then we wrote the definition. And then we realized that we don't need the full power of traversal. So we don't need it for arbitrary applicatives. We only need it for this cons list A applicative. And then we specialized it to this, which means it's more general now, this to list off. It works for more things potentially. Right, and the idea here was we used the cons list A applicative in order to collect all the focused elements in a list. So if I can just just as to remind how it worked. So for example, I can apply it to a lens. So if I have the first component in a pair lens, whatever, character and Boolean, to list off, sorry. Then it basically lists all the focused elements, but of course, _1 is a lens, so it always only focuses on exactly one element. So we get a list with one element. This is maybe now, okay, fine. So the string is a list of one character, the focused character. If I do it for the second, it's the list containing the Boolean. So that's that. But if we instead have a traversal like each, whatever, true, false, true, then it's a bit boring. Then it just, all the focus elements are just the list elements. So I can make it more interesting by composing, for example, with something like this, and then have right. So that was this to list off. So it collects all the focused elements of a list, or of a lens or of traversal in one list. Now, if we are, maybe we are not interested in all of them, but only in the first of them. And that's something called preview. So let me just copy the definition here. It's called preview. And the idea is that we don't get a list of A's, but a maybe A. So if there's at least one element, we will get just that element, just the first one. And if there's none, no focused element, we get nothing. So now, of course, this is not correct anymore. So now I must replace the list monoid with a different monoid, and the one that we saw last lecture, beginning of last lecture, that fits perfectly. Here is the first monoid, which, remember, has exactly that property. It picks the first just, and now I must just import that, I think. That the monoid first. Right. First. So pure I must replace with first and just. And right, this get const. So now I think it's called get first. Yeah, okay. So if I now do the same examples here, instead of to list off with preview, did I reload? So for a lens, for example, if I do now preview, instead of just a list, a list of all focused elements, I get just the first focused element or nothing if there is no focused element. So in this case, there is this exactly one and I get it. If I do preview 2, I will get the just true. And if I do this example, for example, with preview, I will get the first true here that it focuses on. If I have an empty list, And then it complains that it doesn't know which type, but if I help it, then it's nothing because it's the empty list, so nothing to focus on. So just keep that in mind. So we also have this preview. So it's like a slight variation of to list off, just using a different monoid here. Instead of collecting all the focused elements in the list, we just remember the first focused element in the first monoid. Of course, I could do the same for last and only remember the last focused element, for example. Right, so that's this. Okay. And now I think maybe we should have our first break before, maybe just as a teaser what prisms are about. So we have lenses and traversals at the moment. So a lens focuses on exactly one element inside the structure, traversal on arbitrary many of the same type. And but now we also have types like either or maybe that have two constructors. So where there are certain parts that can be there or not. So for example, if we have this type here, we call result A, and it can be, there are two constructors, okay of type A or error string. So if we wanted to have like something like an optic that zooms into this A here, then it can't be a lens because a lens, for a lens, the A always has to be there. But in this case, we also have the error constructor. So if that is used, there is no A to zoom into. Only if the OK constructor is used. Now we could use a traversal for this. So we could define a traversal that traverses all the A's. So it would be 0 or 1. But actually in this case, we know more. I mean, we know the A may not be, maybe there or may not be there, but if it's there, we can reconstruct the complete result from this. Because if we have the A, we can just apply OK to it, so we get a complete result, which is different to like fields in a record. If you know the value of a field in a record, you don't know the whole record. You only know this one field. But in cases like this with several constructors, it doesn't have to be a specific constructor, but if it is, then the information in the constructor arguments is enough to give you the full element again. So in that sense, a prism is stronger than a traversal. So we need something new, not just, traversal, we could define one, but it wouldn't be as strong as we want. So it's so there are two differences to lenses. So in contrast to a lens, the focused element is not always there. So in this case, it's only there if our result used the OK constructor, but not the error constructor. But on the other hand, it's also stronger than the lens, but because if it is there, you can use the information to reconstruct the full thing again. Right, and one could, it's basically in some sense, it's like dual to lenses, same sense. But this is like category theory, so let's not dwell on that. And the idea is now that we can pursue after the break for prisms. We'll do it similar to what we did for lenses. So we start with a naive definition, like a very concrete one. But instead of getter and setter, we will use two other fields to define a prism. Then we'll also show that these prisms are composable. So given prism from S to A and the prism from A to X, you can compose it to a prism from S to X. And then we'll do the same that we did last time, but much faster now, because now we know what we are aiming for, to also write prisms in the same shape that we did lenses and traversals as these weird functions. And as a result, we will then be able to freely compose all three types, prisms, lenses, and traversals with each other. Right, so, but as I said, maybe we should have a break first, 10 minutes, and then we can do this.
Half past?
Yeah, okay, half past is fine.
Okay.
Okay. Okay, should we continue?
Yep, no questions.
Okay. Right. So let's do our first shot at the definition of a prism. So prism SA, prism with two fields, and the first is called preview. So it's basically the getter, but in contrast to the view, the getter of a lens, we now cannot be sure that an A is actually there. Maybe it is, maybe it isn't. So instead of S to A, it's S to maybe A. And now the other part, the reconstruction part. So if we have an A to construct an S, that's called review. So from A to S. Okay. And because it will, last time I first worked directly with this, but then later I had to change code because we changed the definition. So now I basically will write just a synonym for this capital Prism for the constructor, just as another function. So given a preview and a review, give me a prism. And of course, at the moment, the definition is just lowercase prism, that's uppercase prism. Okay, and now we should, right. And remember the lens laws. So get and set had some obvious compatibilities. For example, if you first set and then get, you get what you set and so on. And for review and preview, we also have obvious things. So if you preview, you may find an A or you don't, but if you find one and then review that A, you should get the original. So if previewing gives you an A, then reviewing that A gives you the original S. And the other way around, preview, review. So if you review an A and then preview it, you should find exactly that A. So you review PA, preview it, you get the A you put in out again. So that's the Prism laws. And let's just write some example prisms. So there was this type, what did I call it? Result. So data result A to constructors okay A or error string. Just arriving show. And let's write two prisms, one for each constructor. And the naming convention. So last time I told you that fields in a record, if in the context of optics, often get an underscore before their name, and then the corresponding lenses drop that underscore. And for prisms, it's like dual. So the constructor names, okay and error in this case, don't have underscores, but the prisms then do get an underscore. But that's just a convention. So okay, we use our smart constructor here, this prism. Preview, review. So preview must go from result A to maybe A, and review from A to result A. So review is easy. That's just the okay constructor. Preview, we have two cases. If our result isn't okay, we have found our A, we can return it. And if it's an error, we don't have an A. Okay, and similar, we can define an underscore error prism for the other case. the other constructor. So that goes from the prism from result A to string. So given a string, use the error constructor. And here, if we find an A, we don't have our error message. And if we have an error, we return it. Right. We can try that, of course. What now? Oh yeah, sorry. It's maybe string. Right. So let's try our OK prism. So preview OK. If we actually have an OK value, for example, OK true. So A is bool. We find that true. But if we have error, oops. Maybe bool, for example, then there is no bool in there because it's the error case. Similar, if we have preview error, oops, we find it. But if it's an OK, for example, OK false, then we don't find an error message. And for the review part, we review true. Sorry, review OK true result. We get OK true. And if we review error, boom, must tell the compiler what the A is, for example, int, then we get error boom. So far so good. So that works. Now, okay, I did that. And same same that I said for lenses also applies to this. This is all very mechanical. So the review, for these cases, for these sum types that have several constructors. So the review just uses the constructor and the preview pattern matches. And if it's the right constructor that you are defining the prism for, it gives you the just, and then for other constructors, nothing. So that's again easy but tedious. And what I mentioned last time, that there are tools like Template Haskell to do that automatically for you. That's also true for prisms. So you normally never have to write this boilerplate yourself. So you basically, it's a one-liner, and then you have get all these prisms and lenses automatically. This here is just this naming convention that I already told you about with the underscore. And now I would like you to take 10 minutes again to implement as examples these prisms here. So a prism underscore just that tries to zoom into the A or maybe, underscore nothing that tries to zoom in from a maybe into the nothing. So if it's a just, it would fail to zoom in, but if it's a nothing, it will succeed with a unit. Left and right, the obvious ones, so it looks for a left value or for a right value. Nil looks for an empty list, cons looks for a non-empty list. And finally, the identity prism that zooms in on itself. So yeah, maybe 10 minutes.
Yeah, but before you go, can you copy and paste to the chat the boilerplate so they don't have to rewrite the definitions of Prism?
Oh yeah, that's a good point. Sure. Like this or?
Yeah.
Let's see. Chat.
Thank you.
Welcome. So what's time now? It's
Okay.
22. Is it 22? Yeah, let's say 10 to 50.
50. Yep, sure.
Okay.
Oh, Lars, before you go, can you put on the slide again about what we're asking?
Yes, that would be useful, right?
Thank you.
Welcome. Okay. Should we continue?
Yep.
Somebody has any solutions? Maybe.
If you can share it, yes, in the chat, or at least for some of the functions. I mean, there were a lot, so maybe with just a couple of it's really good.
Sure. Should I just slowly start with implementing them?
Yeah, for sure.
Okay.
I'll keep track of the answers. Yeah.
Right. So what the first one I think was just. It's a prism from maybe A to A. So let me just copy this general pattern here. Okay. So here we go from maybe A to maybe A. If it's a just, we have found our A, and if it's a nothing, then not. So we see this is just the identity in this case, and review is the just constructor. So we can just. Okay. Right now, nothing. So spot a nothing. So, okay. So if we have a just, then we don't find a nothing. So it's nothing. If we have nothing, then we have found our nothing. It's this. And this is just, okay, this is, right. Okay. So what was the next, left and right? Prism either A, B, A. So the review, sorry, preview, let me do it with this either. So in the left case, we have found it. So we can return just the just A. And in the right case, we didn't find the A. And the review is just left to get from A to an either A, B. And why is that not working? Did I already define that somewhere?
No, the type signature is wrong. You need the double colon instead of the equals.
Oh, yeah. Thanks. Right. Okay, the right. So it's just the other way around. So if we find an A, it's nothing. And otherwise, it's just here the right constructor. Okay. Nil constant it. Okay. So that maybe I can write this again. So going from list of A's to maybe unit. So if we do have the empty list, we have found the empty list. And if we have not the empty list, then not. And the review to, okay, just the empty list. And finally, almost finally, the cons. So if we have the empty list, we didn't find the cons case. And if we have a head and a tail, then we have found a head and a tail. And the reconstruction, so given a head and a tail, and build the list from that. Of course, I could also write that with uncons, uncurry and colon. But anyway, and finally the identity lens. So in this case, I always find my A, of course, because I start with an A. So it's just, and to reconstruct, I don't have to do anything. I have the A already. Okay, and I forgot to mention that we also want to compose Prism. So that means we want a category instance. So let's import that again. Okay. Right. So the identity, of course, is just our identity prism. Right. And composition. So going from a prism AX and a prism SA and a prism SX. So prism AX and a prism SA. Prism, preview, review. So preview goes from S to maybe X. And review goes from X to S. Why? Jesus. Yes.
Nice.
What did I now all import? The stupid sorted lint list. Just remove that. Anyway. Okay. Right. So, I mean, obviously, and in this case, actually, the composition is much easier than it was for lenses. So here, I mean, we have an S and we want to find an X. So obviously, we first try to find an A. And if we don't, then we are out of luck. Then, I mean, if we can't even find an A, we definitely won't find an X. But if we find an A, then we can try to find an X. So it's basically just composition of the two previews we have. So one way would be to do that with do notation. So we first try to find an A with the preview of our first one, of the SA one, apply to our S, and then we preview with the other one, the AX one, our A. And why is that not working? Okay, that's again this. Is it scope type variables?
Yep.
Okay, and then I need
there.
right. And if you paid attention earlier today, then one could much nicer write this with this Kleisli composition as well. So that's exactly what it is. So we first do SA and then X. Not sure whether that's in scope now, of course not. So control arrow or monad. Okay, fine. And then the S is gone. Just to show you that it's really nice already. And here it's even easier. I mean, given an X, I just review to get an A and then I review to get an S. So this is just, that is just not even like a weird composition. It's just normal function composition. So review SA composed normal function composition with review AX. So this is already quite pretty. I mean, it shows that somehow the definition is good. I mean, it seems to be like nice and symmetrical and pretty. Okay, and now we can try this if you like. So the composition. So if we, for example, have, I don't know, an either, and let's say we look at the type, for an example, either maybe bool string or something. So I can use the left prism to go to this, and then the just prism to get to the bool. So I can try this. So for example, preview. So the just prism composed with the left prism of, well, if I have something, so if I have a left just true, it will find it. But if instead of a just true, I have a nothing, won't find the Boolean. It's of type maybe bool. It won't find it. And of course, if I have a right something, then it also won't find it. Okay, and of course, for good measure, I could sprinkle in some identities here because they don't change anything.
There was a comma instead of a point in one of the compositions. Yeah.
Oh.
Now
God,
you're outside.
Yeah. That's right. I'm outside. What now? Yeah. Sorry. Yeah, I'm outside Vim. Right. Okay. Okay. So that works. And of course, we could also do the review part. I mean, I can, for example, review false. Same thing. So the same one I had. So just left. I must help the compiler tell it what type this actually is. And then it reconstructs it. Okay. So that's so far so good. And I mean, somehow, I don't know, it's probably, I don't know, but somehow lenses feel more useful than prisms. Probably because you often have these like record types. I mean, that's very common in real world applications that you have user types and all these things. So nested records are very common. Maybe nested, I mean, sometimes are not so common. So this doesn't look as useful as our lenses did, but it becomes particularly useful if you combine prisms with other types of optics like lenses and traversals. Then it's really cool, and we will see examples. So at the moment, maybe it's not that convincing. The problem, of course, is, so yeah, it's just solutions. Some examples. Right. So the problem, of course, is at the moment we can compose prisms with other prisms, but we can't compose them with lenses or traversals because it's completely different types. We have this prism type. And the trick, and I mean, we would have had the same problem last time with lenses and traversals, and the trick was that we brought them into this same shape, right? that it was always functions of this shape, A to FA to S to FS, and then just with different constraints here, functor or applicative. And that also gave us a type of subtyping, basically, because it immediately shows that every lens is a traversal. Because if something works for every functor, it works in particular for every applicative, because every applicative is a functor. So that was very nice, and it basically automatically guarantees that you can compose these things. And that if you compose a lens with a lens, you get another lens. But if you compose traversals or traversals and lenses, you just end up with a traversal. So that's all beautiful. And now, of course, the plan is to also put our prisms into this form somehow. So also something of this shape, so that we can freely compose them with lenses and traversals. However, it's a bit unclear how to do this. I mean, a lens focuses on exactly one element. Traversals focus on arbitrarily many elements. A prism focuses on 0 or 1 elements. So a prism should be a traversal. So it should somewhere be here up above the traversal. So every prism should automatically be a traversal. I mean, a traversal can focus on 0 to arbitrarily many elements. A prism always focuses on 0 or 1, but that's a special case of applicative. Sorry, not of traversal. On the other hand, it's also not weaker than lens because it has this review. If you have a lens, given the part, you can't reconstruct the whole, but with a prism you can. So it's not really weaker or strong. I mean, it wouldn't fit here. If it was here, that would mean that every lens is a prism, which is not true, because if you just have a field in a record, you can't use it to reconstruct something. But we also can't put it above here, because that would mean every prism is a lens, which is also not true, because the aim may not be there. So somehow it doesn't fit here. We need something different. And also it's not clear, I mean, what to do here with this functor applicative thing. First of all, we don't need know any type classes that are somewhere here in the same hierarchy, but in between. I mean, monad would be down here, and it doesn't fit anywhere, as I said. I mean, if it's something between functor and applicative or like weaker than functor, it wouldn't fit. So somehow it looks as if we are out of luck. I mean, we don't know where it should go here, and we also don't know what we could put here for prisms to make that work. And the trick now is to rewrite this a little bit, and this now leads us back to earlier today. So we rewrite this arrow and this arrow. We rewrite that in this form. So just prefix. So this is just a syntactic change. I mean, this stays a normal function error. I mean, these are also still normal function errors. We just write them funny. So instead of writing them infix like normally in between here, we just write them prefix. And the idea is to now get the inspiration that there is something else we can change. So for lenses and traversals, we always had the function error here. And now the ingenious insight, I don't know whose it was, maybe Edward Quett or whoever invented this. Now the ingenious insight was to, instead of using the function error here, allow other profunctors. And that gives us more wiggle room to fit prisms into the scheme. So the definition that falls out of the sky, so I have no idea how to like explain how one would ever come to this idea, is to do this. So we basically use applicative for the F, like for traversals, but we then use choice for the profunctor. And I mean, I'm not claiming that that is obvious, but we will at least see that it works, and that we can get from this weird description back to our naive one with preview and review. But before we do this, let's just taking that, I mean, accepting this definition for a moment. We already see that it fits nicely with what we said. So if now Prism is applicative and choice for the profunctor, we see that every prism is a traversal, because if it works for every applicative and every choice profunctor, it in particular works for the arrow choice profunctor. So prism implies traversal. That's already nice. And we also see that it's like neither is a lens a prism nor is a prism a lens in general, because lenses work for every functor, but only for arrows. So it's neither stronger nor weaker than prism. So prisms are stronger because they work for arbitrary choice profunctors, not just for the function arrow. But lenses are stronger because they work for arbitrary functors, not just applicative. So we see that, I mean, even without understanding that, I mean, how one would ever come up with this, we see that it fits nicely in the hierarchy. So it's, I mean, both prisms and lenses imply traversal, but prisms and lenses each other, I mean, there's neither is the one the other or the other the one. Right. So that's the definition. And now let me just write it down. So we remove this one. And now the definition will be type prism SA. How did I exactly write it there? Okay. For all FP, applicative F, not profunctor choice P, which in particular is profunctor. Okay, and now I need to import this. So I could import the one I did earlier. Let me just import it from the profunctors package on Hackage. And let me also import profunctor from there so that we have our die map. Okay. So if we have something from P, P A F A, we can go to P S F S. Now it will complain about rank N types. Yeah. Okay, so this is our new definition. And as I said, it's like completely magic, I think, how anybody could come up with this. But we will see now that it actually works. And the first question is, I mean, if I now do this and reload, then of course I will get errors. Okay, first of all, we don't need this category stuff anymore, because as before, once we have it in this shape, it's just a function, a normal function. We can just freely compose it. So that's nice, and that's the same nicety that we had for lenses and traversals as well, so that's good. Right, but now of course this doesn't work anymore. But now to basically start believing that this is the right definition, we will now just try to do this. So given a prism, I mean, given preview and review, construct a prism, which now has this definition. Okay, so let's try this. So we have a preview and a review. And we have this thing. So let's call it, I don't know, what did I call it in the slides? Okay, let's call it X. I had different names in the slides, but doesn't matter. Right, and this looks now like completely hopeless. I mean, because this is all very weird. I mean, we don't really have a feeling yet for choice, what that even means. Profunctors are also new and mysterious. And so it's totally unclear how we can possibly do anything. But actually, this is again an instance of what I said like many times now, that often if something is very abstract and polymorphic, then it's actually easy because there's not much you can really do. And I mean, in this case, I mean, we are supposed to generate something in this profunctor. We don't know anything about the profunctor. Could be anything, something weird. So the only thing that we have at our disposal is DIMAP and these left and right, because we know it's choice. I mean, that's all we can possibly do. And I have this beautiful diagram here that explains it. So let's try to briefly go through it. So this basically, the diagram explains how we can actually do this. So this is what we have. I mean, I write these squiggly lines for profunctor. So it's not really, it doesn't have to be a function, right? I mean, profunctor, we know, I mean, function is one example. It could be a Kleisli error. It could be tagged. It could be anything. But nevertheless, in this diagram, so the squiggly line is supposed to be profunctor. So this is a PAFA. So that's what we start with. And this squiggly line here is what we need. So we need something, a profunctor PSFS. Okay. And so how can we possibly get there? And this diagram explains it. So first of all, because it's a choice profunctor, we have the right prime. So given this thing, by definition of right prime, we get this. So a P from either SA to either SFA. That's just the definition of right. Okay, and now the idea is to use DIMAP to go from this to this. So we have to, so let me just start writing. So we, sorry, here. So the idea is first we use right prime X, and then we use DIMAP with something. Okay, so that's already looking good. So it's the right type. So just now we need to do this DIMAP thing. So we need something to pre-compose it with from S to either SA, and we need something from either SFA to FS. Okay, so for this latter part here, because it's an either, we need something from S to there and from FA to there. So I can use this. Right. So we need something from S to there and from A to there. Okay. So how do we get from S to FS? Well, we don't know anything about F except that it's an applicative. So we do have pure. So the only thing we can possibly do to get from S to FS is pure. So this is pure and we have no other choice there. Now here from FA to FS, well, this is now where the review comes in. That in the slide here is RV. In the code, I just called it R. So we have something from A to S, the review. And because F is applicative, F is in particular a functor. So we can Fmap to get something from FA to FS. So I can do this here. Fmap review. Okay, this is nice. So we are almost done. Now all we need is this arrow here from S to either SA. And of course, one could use left, but that's not the right choice in this case. So this is the only part actually. I mean, all the rest is the only thing we can possibly do. So nowhere did I have any choice because I don't know anything about F and I don't know anything about P, except that P is choice and F is applicative. All this stuff is completely like automatic and forced on me. But here now I do need some like understanding. And of course I could use left. But if I use left, that would be the wrong choice. And an indication why it would be wrong is, I mean, I have used the review here, but so far I haven't used the preview actually. And obviously that can't be right. I mean, that's important information, the preview. So somehow I need something here that uses the preview. And the idea is that I will, I mean, let's call that PR prime. So it goes from S to either SA. Prime. And the idea is now that I actually make use of my preview. So I check whether I have an A or not. So I apply my preview to it. And I think this is again scope type variables. So if it's a left, so I don't find an A, I just find an sorry, I don't find it's not an F, it's maybe. So if I don't find an A, I have a nothing. Well, then I really have no choice. In order to produce this, I don't have an A, so I have no choice but to use left S. But if I do find an A, well, then I can use it to give a right A. And this is what I can use here. So actually, I should call it P prime now because I also call it the preview. Cool. Okay. So, I mean, this is, I think, a nice example of, I mean, this is often how it works, how strong types and a strong compiler and all these abstract type classes and types can guide you basically through an implementation. So in principle, almost everything of this, this is the only way. I mean, if it works, then it has to be like this. I basically have no choice anywhere. And these intimidating types like or classes like choice and applicative and so on, they help me actually because I only have a handful of constructs that I can use. I can only use DIMAP left, right, and pure and app in principle. Okay, so that's that. So now we can go from our naive prisms, I mean from preview and review to something in this weird form. Right. Okay, and now, of course, we also want to go the other way. So this is the one way that given a preview and a review, we can get something of this shape. Now to go the other way, given something of this shape, we would like our preview and review back. Now, if you recall a bit earlier in the lecture, the preview I already defined. So we already have that, and that worked for arbitrary traversals. So we use the, this is an applicative because first is a monoid. So const first A is a monoid. So it's, sorry, const first, because first A is a monoid, const first A is applicative. So it's a traversal. And as profunctor, we just have, I mean, as we always had until just 5 minutes ago, the arrow. So it's a traversal. So it works for any traversal. So this works for any traversal, but it also works for, in particular, then it works for prisms. So the preview I don't even have to define, I already have that. What remains is the review. So I need to define the review, but I must import this. So let's import that. So our stuff from last time. Okay, and now all that remains basically to convince ourselves that this and this weird definition are actually equivalent, more or less. I need a review. So review, so given a prism and an A, I want to be able to reconstruct the S. Just I hate it so much. Okay. Okay, we have our prism and we have an A. And right now, basically it's creativity again. I mean, we can use now we can choose the applicative and we can choose the profunctor. And the idea here is to use the identity applicative and the tagged profunctor. So idea use F identity and P tagged. Right, and I think I have an example. No, I don't. Okay, I don't have a diagram for this. So let's see. Prism. So if we specialize that to what I just said, so we get something. So P is now tagged. So we have tagged A identity A to tagged S identity S. And remember, tagged is just basically it just contains the second value. So I mean the value is just identity A, identity S, and identity is also just a new type. So it's really just a function from A to S. So now I must just do this right. So I must just apply this prism that I have. So the function, to what do I apply it? To this. So tagged identity A. And now I get something of this type, and I must just unwrap everything. So first I untag it, and then I run identity. And what's now the problem?
You have imported twice the tagged and untagged
Okay.
for some reason.
Yeah,
Yeah.
Isn't that there? Ah, okay, sorry, that's somewhere else. Let me just find it. I thought it was in ProFunctor, but it's obviously not. Tagged package. I think that's it, I hope. Okay. And does it have the right instances? No idea.
No.
It's the wrong one.
Yeah, maybe the second link was the right one.
Right.
Google.
Uh,
There.
can also just use a look in lens. Let me look in lens.
Maybe you could just Google it.
Yes, can do that as well. Just one. Oh, no, sorry. Yeah, review. Must just find review, right? Review. Review, tag. There's tagged. Tagged. Well, it's called tagged. That is the right one, whatever. I just didn't see the instance then, it seems.
No, me neither. Must be somewhere.
Must be somewhere. Maybe it's
I saw the
included
traverse. Yeah.
in by traversable or whatever. Anyway, okay, so I need this tagged package. Because I could also define it myself. I mean, which we did, but right. Was so it's in data dot what was it? Data dot tagged?
Yeah.
Okay. Right. I also need identity. Okay, right, now it compiles. Where was I? Here, right. So that works, and of course I can write it nicer if I like. Eta reduction. So it looks much more complicated than it is because of these new type wrappers. I first have to wrap it in identity and tagged, then apply my P, and then unwrap the tagged and identity again. But in principle, it's exactly the right thing already, as I showed here. So it's just these two wrappers around it. Okay, and now we can do the same trick again that we did for last week for view and preview and so on. So instead of doing it for an arbitrary prism, I can just do what I need. So I don't need the full power of a prism. I don't need it for all pro functors, and I don't need it for all applicatives. I only need it for identity and tagged. So I can do this. So I can replace that with for all as a P. So instead of P, it's just tagged a identity a to tagged as identity s. What's now? Ah,
Because it's inside the parentheses.
yes. Right. This, I think. Fine. Okay. Right. So now we can also go back again from, I mean, so now we have it in both forms. And this I don't need anymore because composition we get for free. Right. So now I put it in this form. And again, I have my constructor Prism. So this was now, I mean, this complicated diagram. But now that I have it, all the definitions we did or you did earlier still work because that didn't use the constructor directly, but it used the smart constructor Prism. So by changing that, now everything still works. And we should also be able to go back from, I mean, from a Prism in this form, we can now go back to preview and review. So we have preview and review again. Preview because that we have for every traversal, so in particular for prisms, and review because we just defined it. So hopefully, I mean, all the examples I did earlier should still work. I still have them somewhere in my history. No, I'm not even in the REPL, of course not. Okay, fine. What was that? I mean, something like preview. So whatever it. Yeah, but one thing is, as before, last week when we switched from our naive definition to this Van Lahoven style, the order of composition changed to become like in object-oriented programming. So that's the same now again. So now it's the other way around. So if I first want to go left and then go into adjust, then it's now this way around. Left, just two. Right, so that still works. But now what we gained by using this complicated definition instead of the naive one is that we can now freely compose it with everything else. For example, with lenses and traversals. So for example, we could have, let's see. For example, let's say we have a pair, I mean, this type bool, and then a list of, I don't know, maybe maybe either pool Okay, so for example, false, then nothing, just left true, nothing, just left false. Maybe before we have a just right Haskell, and another nothing, and the just right Kenya. Okay, just some weird data type. And now I can freely combine that and, for example, change every letter in the strings to X's. So I can, what was the set? So set takes the lens, or I mean the optic, then the old value and the new value. So I can now do set. Okay, so I want to zoom into these strings. So first I use the _2 lens to go into the second component. Then I use the each traversal to go through each element in the list. Then I use the just prism to zoom into just values. Then I use the right prism to zoom into the rights of the either. And finally, I use the each traversal again to go to each character of the string. My example, let's set it to X. And it picks out the Haskell and the Kenya and changes each to an X. Or I can target these booleans and apply a function to them, like not. So I can do over not example. But now instead of targeting the rights, the strings, I target the lefts. And now the left true is the left false, and this left false is the left true. Right, so the true power only, I mean, as I said, prisms by themselves are maybe not so wonderful, not as impressive as lenses, but in combination, because they allow you now to really drill into everything. Because even if you have something with several constructors, like, I mean, maybe or either, so then the prisms allow us to do all of that. And of course, also the to list off, for example, still works. So we do here to list off. Then we get all the characters contained in here. So the HASKEL and the KENYA. And if we use the left one, we get all the booleans, true and false, for example. Or whatever. I mean, we can also focus on the nothings instead. Not very interesting, I suppose, but we could. So we find the 3 nothings here. Anything else fun?
I think modifying the strings is already fun. So
Yes. Yes, I think it is. Oh yeah, one last thing. Using this cons prism. So just a second. Let me just import data.character again. So we had this one that focuses on each character. But instead, if I leave the each, so then it focuses on the strings. The strings are lists of characters. So now I can compose that with our cons prism, which only focuses on non-empty strings. In this case, we only have non-empty strings, but maybe let me change that and let's just add one empty string as well. And okay, so now we have all the non-empty strings in the form of a pair of head and tail. So now I can, for example, go over and apply the function. So given a head and a tail, it just let's say to lower x, and it leaves the tail as is. And now it turned the words to lowercase. So or I could also do maybe map to upper here. Right. So now it leaves the empty string alone. Where is the? Oh yeah, I didn't. Sorry, I didn't reload, so the empty string is not there. Okay, so it leaves the empty string alone, but the non-empty strings, now it applies this function. So it makes the head small and the tail big. Yes, so now you basically have full control over everything that can be thrown your way. Let's see. Yes, so now we saw examples. Probably here's another example. I don't know, should we have another break or?
Yeah, maybe because we already, like last time, it was for an exercise, right? The last
Yes.
for an exercise.
Yes.
Maybe they can.
Yes. So let's have another break then until, I don't know, what's the time. It's
10?
42 until I don't know 55 or.
Yeah, sure.
Okay, right. Let's do this.
Yeah.
And then, okay. Can we continue? Can we continue? Hello, can we go on?
Yes, I can.
Okay, you can hear me. Okay,
Yeah.
good. Great. Right. So, sorry. So one optic left that I've mentioned before, ISOs. So until now we have this diagram basically. We have lenses, traversals, and prisms. And a lens is a traversal, a prism is a traversal, but lens and prism are not compatible with each other because a lens always finds an A, whereas a prism not necessarily finds an A. But on the other hand, a prism given an A always can reconstruct the S, whereas with the lens that's not true. So they are like incomparable. And now there is a fourth type of optic called ISO for isomorphism. And that will complete this diagram at the top. So we get this nice diamond shape. And an ISO will be a lens and a prism. And after all the work we have done so far, defining ISOs is quite easy. Actually, if we look at the definition of Prism, so Prism says for all applicatives and for all choice profunctors, whereas lens was for all functors, but only for arrows. So the obvious definition to get something that's both a prism and a lens is to combine those two. So we define ISO. So by using functor here. So because it will work for all functors and all choice profunctors, it will in particular work for the arrow profunctor. So each ISO is a lens. But because it works for all functors and all choice profunctors, it will in particular work for all applicatives and all choice profunctors. So each ISO is a prism. So with this definition, it's already obvious that we get something in the of this diamond shape. So ISO obviously implies both lens and prism. And now, of course, the question is how to like define ISOs. And actually, so then we need something basically like this. So ISO. And the idea is to define it with a preview and a review. So an ISO given something that always finds an A, so that's like the lens part, but also something that given an A gives us an S, we will have an ISO SA. So it just means that S and A are basically equivalent. So it's like it contains the same information. So the let me just check on the slides. So we want to fit it in there because an ISO is a lens, and for lenses we had view. So we in particular have a view, but because it's also a prism, we also have review. And the idea basically, or you can think of it, it zooms in to an equivalent part of itself. I mean, it's not really a zoom in this case, it's more conversion. So S and A are basically two types that contain the same information, and with view and review, you can convert between the two. An example we have seen last time already, lazy and strict byte strings. So you can go back and forth between lazy and strict byte strings, and so that will be ISO. And as for lenses and prisms, you also have laws for ISOs, and they just mean that if you go back and forth, you don't change anything. So if you first view and then review, you get the original S back, and if you first review and then view, you get the original A back. So in both directions, view and review composed are the identity. Okay, And so we get to this definition, and now we want this function. And this is again one of those profunctor exercises, but it's much easier than before. So see, right. So we have something A to FA, profunctor, and we want something S to FS. And so let me just write that. So ISO view review and some PAFA. So now we need a PSFS. And again, I mean, we don't have much at our disposal, even less this time. I mean, earlier we had, if we were with prisms, we had that F was applicative. Now F is just a functor, so we have even less. We only have F map. And we have the choice stuff, so left, right, die map. But actually it's very easy in this case. So we just need die map. And on the left, to get, I mean, we need something from S to A and something from FA to FS. So let me just write this. So die map, two things, and then our P. And yes, we can even remove the P. So we need something from S to A, which we have. It's our V. And we need something from FA to FS, but we have something from A to S. And F is a functor, so we can just F map our R. And right. Okay, and that's how we can define ISOs. So given an ISO, we get the view and the view because it's a lens, the review because it's a prism, and given a view and a review, we can construct an ISO. And finally, I mean, ISO, obviously the S and the A are equivalent. So we also have something that is called or revert or something like that. So given an ISO from S to A, we also get an ISO from A to S. Somebody please delete that stupid sort list. So given the ISO, we just use our ISO, and now we must just swap review and view. So the view of this reverted ISO is the review of the old one, and the review is the view of the old one. So that's very simple. Right, that's here. And now we can like look at the first, I mean, as I said, we already had an example with this lazy strict, but let's look at another example. Let's call it maybe to either. Okay, now. So maybe to either an ISO from maybe A to either unit A. I mean, when we talked about monads, when we introduced monads, my first example was maybe, and I said that's like the side effect of exceptions, but just exceptions without error message. And then we said using either E, we can basically enhance that with error messages of type E. And then, of course, if for the type of error messages we just use unit, it's exactly, I mean, it's the same thing as maybe basically. And this ISO will express this. So maybe to either, so ISO view review. Okay, view, we must go from maybe A to either unit A. So if we have a nothing, we do left unit, and if we have a just A, turn it into a right A, and review other way around, either unit A. I could write it with either again, but I can also write it explicitly. So if we have a left unit, just goes to nothing. If we have a right A, map it to just A. Yes. Okay. And now we can, if we like, play with it. So for example, I don't know. I mean, view. Let's see. So we have maybe to either. And so we get from a maybe to an either. And now we can compose it, for example, with the right lens. Apply it to just, I don't know, true. We can do preview. Can't, why not? Confused. Second. Just parentheses were wrong. Right. And can also do this to go the other way. And just okay, not very exciting, but again, in combination with other optics, it's maybe more exciting. And actually, there's a couple of exercises again for you to implement some ISOs. So maybe, I don't know, 10 minutes again.
Yeah, and if you could also provide the
Yes. Right, that's basically the whole file, right?
Yeah, maybe just the definition. Yeah, the whole file.
But it doesn't matter. I mean, I suppose
Just the definition of ISO, Prism. Yeah.
let me just a second. What do we need?
All right, but
I mean, basically, we only need those two things.
yes, but they need to have the libraries as well.
No. Oh, yeah, you mean?
Yeah, to have access to DMAP, MNFMAP, functor choice. Functor.
Yeah, true. Maybe we should just leave it then, the exercise. I'm not sure.
Yeah, maybe we can just keep going.
Yeah, let's do that. Okay, fine. Just a couple of examples. And for some reason, I mean, there are always these naming conventions. So, I mean, for lenses, we had this, that basically it's like the field names without an underscore. For prisms, it's the constructor names with an underscore. And somehow for ISOs, it's often with this, like, what's that particle? I don't know the English term for this grammatical construction, but it's like reversed, carried, flipped, swapped, something like that. So reversed would be an ISO from list of a from what did I do now?
Functors now.
Oh, yeah, okay. I don't know why it's what I changed there now. Did I delete anything important? I think not.
No idea. You just close.
Right. So the idea is the isomorphism, that a list and a reverse list, that's like isomorphism. So reverse is iso, and of course reversing twice is, why is this now not prelude, more optics reverse? Oh, reversed. Okay. Right. Just as an example, so if we do what now? I probably messed something up.
It was the name
Yeah.
of the functor.
Yes, yes. In the pro functor, it's still called more optics. So let me change that again. Okay, that should be fine again. Okay. I mean, if we have the normal, I mean, for example, with each and I don't know, first, so preview. So if you do preview each Haskell, then we get the H, the first focused element. If instead we do preview reversed and then each Haskell, then we get the L, because it first reverses it and then does the each. So it traverses the list in the other direction. So that's reversed. What else did we have? Curried. ISO from function from pairs of A's and B's to C's to curried functions from A to B to C. And that's of course just, I never know which is which, uncurry curry. No, other way around.
Yeah, the other way.
Also not, yeah, okay. Like this. So curry and uncurry are just convert between those two. What else did we have? Flipped. So if I have something from A to B to C, I get to B to A to C. So that's just the flip. I mean, flipping twice gives me the original back. And then I've swapped. So swapped is just ISO swap, but swap is not defined in the base libraries, I think. So swap A, B, B, A. So for example, I could do, if I do view the one lens of a pair Haskell and true, I get the Haskell. But if I do my swapped first, then I get the true, which of course is in this case the same as when I just used the _2 lens in the first place. Okay, and finally we have this swap prime for either. So it's just as simple. Okay, just some silly examples for ISOs. I mean, the more useful ones are, as I said, this byte string, for example. I'm not sure whether I still have that here. Lazy, let's see. Yeah, I still have that. So back then I defined it as a lens and lazy and strict. Not sure I can, for example, delete that here, put it to more optics here. Right, I must import those two. Byte string. And then need this. Okay, and now I can actually make it an ISO. I'm not sure whether that would then be called lazy or whatever, but so an ISO from byte strings to lazy byte strings, and it's just BS from strict BS to strict. And strict is also actually an ISO. And I could, of course, define it the other way around, but I can also just say it's relazy. Okay, and now I could like go back and forth between them if I wanted to. The same we could do for text and string, for example. Maybe why not? It's maybe even like at least easier to play with than with byte strings. Let me just for text. So I could do import qualified data dot text as t. Then I could do packed. It's an ISO from string text. Packed. It's just ISO. Go from a string to a text, we can use pack from the text library, and to go from text to a string, we can use unpack. And I could do unpacked ISO text string. Right. And now I have a text. So let me do set -x overloaded strings. And let me define t as Haskell of type text. So t is of type text. And I mean, in the text library, there are ways to also manipulate characters, but it's easier to work with strings, right? So one thing I can do, or maybe not, but it's just an example anyway. So now, for example, if I want to, I mean, the usual map to upper on T won't work. It won't work anyway because it's not in scope, but the usual one won't work because, I mean, map to upper expects a list of characters, but now I have a text. But what I can, of course, do is let me just think. Right. I mean, it's not ideal, but I could do. Yeah, actually, that is ideal. Right. I can do, for example, over. So now I use my unpacked. So now I have a string. Now I can do each and to upper T. And now it's, but the type of that is a text again. So basically I unpacked it to a string, then that was easier to work with, loop over all the characters, apply to upper to it, and everything is taken care of. So it's basically unpacked to a string, the operation is done, and then it's packed back into a text again, and this all happens automatically because of our mechanism. Of course, I wouldn't need to do that. I mean, there are functions in the text package that allow me to do something to every character in a text as well, but just as an example. So this would be inefficient, what I did here, but it's just fun, I think. Right. Are there any questions? Otherwise, we can come to the last topic for optics.
No questions yet.
Okay. If we look at lenses again, or any of our optics, or let's say look at traversals, and if we remember the type of traverse from the traversable class, let me just write that here. So that's, I mean, if I have traversable T, and yeah, replicative F, and this is how we got our inspiration for traverse. Doesn't matter. Then it's actually it's if you have something from A to FB, then traversable containers allow you to go from a container of A's to F of a container of B's. So that means traverse can change the type. For example, I can, let's say I have a list of strings, and I can traverse the list with whatever. A string goes to, for example, with length, and I need an applicative. So for example, put string line. Or let's say, so a string goes to, first I print the string, and then I return the length of the string. And if I now traverse a list of strings, then I end up with a list of ints, right? Because this is a function from string to IO int. So A in this example is string and B is int. So I end up with IO list of ints. So the IO actions were to print the strings on the screen, on the console, but then I get the list of lengths. And in our traversal, we can't do this because we have the same A here. So we can change something. We have over and set, but we can only change to the same type again. And now the last step in our lectures on optics is to lift that constraint so that we can also change the type where it makes sense. And this means now this looks horrible, but so there will be 4 type parameters. And I always remember it because it's step, like a word, to step somebody. And the interpretation is, so I have an S with some A inside. And if I change that A to a B, I will end up with type T. So luckily this doesn't, we won't have to change very much to do this. So it just changes here. So I change an A to a B, and then the S changes to a T. So that's the final definition for lens, and same for all the other optics. So we always add these 2 other type parameters and change accordingly. And but often this what we had earlier is still useful. So there is normally people define type lens prime SA. That's our old lens. So it's where S and T are the same and A and B are the same. So, and same for, I think, for traversal prime. Right, now we probably get a couple of errors, but hopefully not too many. So let's see. Let me load this and let's see what all we get wrong. Okay, let's just fix one after the other. So this is now, I mean, we had this both traversal, and we also have the each. So let's start with each. So we have a container of A's. So there are A's inside. But if we change the A to a B, we end up with a container of B's. So that already just by, I mean, the implementation traverse is still the same because we just saw that traverse already had this generality. So this was easy. Now, if we have a pair with two A's in it, so the same type, so we can traverse both A's. So if we now change A's to B's, we end up with a pair of two B's inside. And we see to our delight that the implementation is still, we don't have to change anything. It still works. Let's see, next error, 105. Okay, we have a pair of an A and of a B, and we focus on the first element. If we now change that, let me not call it B now because we have a B already. Let me call it A prime. So if I change the A to an A prime, I end up with a pair of an A prime and a B. And the same here. If I change the B to a B prime, I end up with a container containing A and a B prime. So to our delight, this still compiled. So the complicated definitions or more or less complicated definitions we did last time still work. Here, this was this example. And here, I think the easiest is to just use this lens prime type. So here, it doesn't make sense to change the result type. So that's just lens primes. Okay, lens. Okay, our definition for lens. So now the getter still gets an S and returns an A, but now the setter gets an S and a B and returns a T. And that gives us then a step. Again, the definition just works. So this all works. Let me think about the add. I think that doesn't make sense to change types because I mean, by just manipulating one element, we can't have a map with different types of values inside. So this will still be a lens prime. Oh, looking good. Okay, so now optics is already fixed, which is, I think, also quite cool. That everything we did, we could have done it in this generality immediately. So and we didn't have to change a single implementation. So all the implementations still worked as before. All we had to do change the signatures a bit. So now let's switch to the more optics stuff from today. Right, there, of course, everything is still working anyway, but now I'll do the same change here. So it's a step prism. So PAFB, PSFT. And the same for ISO. ISO. Step. So PAFB, PSFT. Right, I think fixing ISO is easier. So now we view an A, but we set a B and a T. So to our delight, again, this also still works. And now we do the same, that we define ISO prime SA as ISO SSAA. So I think all of these examples just ISO primes. I don't even know a good example of ISO, but anyway. Actually, I suppose we could just see here, for example, I suppose we could, I don't know. Let's keep it at ISO prime, I think. Right. Was a bit cheating, but anyway. Can't really think of a good example that's an ISO without prime. Anyway, now prisms. First of all, let's do this definition with the prime as well. So the simplified one. Prime SA is prism SSAA. Okay, we do have to do something here. I mean, now we see an A, but now we have a B and want to get a T. And now we see something doesn't work. Okay. What does it? Actually, I'm a bit surprised it shouldn't work, I think. Let's worry about that in a second. But here, that should just work. Let's just do this. Okay, now it's ABST. Preview still works. Okay, these are now. Here I can actually. So if I have a result A, it zooms in on A, but if I change the A to B, I get a result B.
Lars, we have a
Yes.
question.
Yes.
I probably missed it, but what more power does ISO give us? So why are we using ISO is like renaming everything, basically?
You mean ISO itself, or now in the context ISO versus ISO prime? Because yeah.
Yeah, I mean, the question is a bit vague, but I think maybe ISO itself is saying, Tony.
Okay. Well, I mean, there was this example that I did with text and string, for example. So, I mean, for example, maybe strings are easier to work, or I mean, yeah, I mean, in my example, I said that strings are easier to work with than text. So if you have a text and you want to manipulate it with an optics, you can use, I mean, first use this packed ISO to get the string, and then like use each or whatever to go over each character and do something. And so that's one way, I mean, or one reason why ISOs are useful, because maybe one form of data representation is easier to work with than another. So you can use an ISO to convert it into the other and then do stuff. I mean, that I think was quite a good example, the packed the text and string. But of course, I mean, the same is probably true for the other examples. Where sometimes it's easier to work with one data representation than another. Try to think of another example. ISO. I don't know. I mean, for example, you could think of an ISO that takes I don't know, a number and converts it into a list of digits or something, and then you could traverse the digits and do something, and then stuff like that. or what else?
I'm not sure, but maybe sort of like an abstract syntax tree and the serialized representation, so you can like transfer and get the serialized like use ISO to modify the abstract syntax in some way and resend it.
Yes, although of course byte string, I mean the serialized representation is not isomorphic. I mean because they are invalid bytes. I mean byte strings that don't correspond to.
Yeah, you're right.
I don't know. I think it's maybe also just conceptually. Actually, we can look at maybe in the lens library. Lens package. Maybe there's some cool examples. Not really a split. I mean, there are examples here.
They are like simplified, so it's easier to understand. So maybe they are not so impressive.
Yeah. Okay, some of the examples we also had. Yeah, I don't know. All the examples look a bit esoteric, I must confess.
Yeah,
So I'm not sure how useful it is.
right. Yeah, we lack a lot of context. We don't have like a use case with stuff like that, so it's harder to come up with.
Well, this is maybe quite useful here, this coerced. I mean, we don't know what, for example, I mean, maybe don't want to go into coercible now, but I mean, for example, a new type and its underlying type. I mean, if you have, I mean, we could have another example here. So now I'm not sure because now nothing compiles. But I mean, I could write a, if I have some new type, whatever, some, or I could have an ISO from A to some A, for example. So to get to some, it's just a constructor, and is it get some, I suppose? Suppose I could turn this into fully fledged ISO, right? And so that's actually an example for a change, right? And you could do the very same thing for any new type. I mean, it didn't use any special features of some. So whenever you have a new type, then you can use this. And I mean, we saw that, I mean, earlier here, for example, that these new types are sometimes a pain because you always have to like wrap and unwrap, and that even though it's simple, it's confusing sometimes. So that would be one use case for an ISO, that you can just using the, or yeah, in actually the other way around. So So if I have some, I mean, something with some, and then it's maybe easier to work, I mean, to unwrap the new type. So as I said, it doesn't have to be some, it can be anything. So by unwrapping the new, I mean, and using this isomorphism, I can easily wrap and unwrap, I mean, in both directions. And then easier work with it. So for example, if I have a list of sums, I mean, I could now do something like whatever over each resummed plus 3. And if I have like sum 1, sum 4, and that would then be sum 4, sum 7. So I don't have to worry about the, I mean, to unwrap it with get sum at my 3 and then wrap it with sum again. This would just be taken care of. Why this is now, yeah, because it's not valid text. We can try this example out once everything compiles again. Yeah, I think that is actually a good example. And this here is very, very, I mean, this cursor basically knows that the new type and the wrap type are the same at runtime. So that works automatically. So this coerce from the lens library would automatically work for arbitrary new types. So I don't have to define my own one like I did here. The summed, it would just work for everything like this. So that's actually nice. So it's easy to, I mean, it can be tedious to wrap and unwrap new type wrappers. And that is, I think, one nice application of, yeah, of this, of ISOs.
Yeah. Tony says thanks.
Come.
Tony says thanks. Thank you.
Okay, welcome. Okay. So now let's see. So first of all, so let's just fix these things. So I did fix the okay. So then I have, so I can't change the string here because that was fixed. So this is a Prism prime. But with just, I could change the A to a B and then I would end up with the maybe B. Nothing is, I can't change this, but I could change this to another type. Left, okay, if I change the A to an A prime, I end up with an either A prime B. Same here. Either A B prime. I think this is the same as maybe. Okay, if I change the A list of A to B, list of B, then I end up with the list of B's. Well, yeah, if I change the A to a B, end up with the B. Maybe to either. Okay, if I change this either unit to B, then I end up with a maybe B. Let's just have this. Okay. Okay, made a mistake. What's the problem here? Wrong import. Just a second. Maybe I made a mistake there. Let's see. Okay. The type signatures. It's B, 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 B.
We have an arrow at the top. There.
All right, that's good. That's good because I was waiting for that. There's problem here. Let's see. Let me just. Maybe view. I have view. View is probably not general enough. Right. 8. Hang on. This must now be a B, and this must be a T. Does it fix it? No. Second. Okay, this is this we have to fix. That's the only real problem. But now I'm just, what's wrong with view? Oh yeah. This I must still change the review. So it's A B S T. Right. I thought that fixed it. A B S T. That's correct. That's one problem, by the way, with lenses. I mean, everything is beautiful, but if you get an error message, it's impossible to understand it. Maybe I check what the whether view is right. Just a second. Unfortunately, I think it's not called view here. It's a different one, I think.
But you have review there, so maybe if you open that one and you go to a bit to the top.
Problem is that this is all like super general. It's much more general.
In the explanation, there's around a view. That's a link, I think. There.
This one?
Yeah. If you click. Yeah. Seems somehow for view there is no. Maybe for. No, but must. I mean, view. I can define view. View is fine. I mean, it just. Fix again. This is now okay. Yeah, that's okay. So this file is okay.
I suppose preview is still wrong. Maybe that's it. So right. I mean, this must also be V and T. But that unfortunately also doesn't fix it. Ah, now it's fine. Let's see, then maybe now everything is good. Yes. No, now this is wrong again. Dread. Maybe it's BATS. Yes. Okay.
But
Okay. Right. Okay. This is just one tiny thing now, and that's, I mean, okay, I did struggle, of course, but hopefully you will agree that it was more or less mechanical. So I just had to change the type signatures everywhere, and I didn't have to touch any of the implementations of anything I'd done. And the only exception is this. And the problem is that now that we are able to change types for the preview, it's no longer enough to, this type is too weak, basically. And the problem is that if we find an A, it's fine. But if we don't find an A, we somehow still need to be able to give a T. I mean, to change it into a T. But there's no way with this signature. So the trick is to actually, and I should say, if we go back to the slides, when we construct this interesting diagram here. So we had this preview of type S to maybe A, but then here I actually used something I call preview prime, which I defined like this, and which goes from not S to maybe A, but S to either SA. And now this S is a T. And what I did was I did the preview that was given, and if I find an A, I use write A. But if I don't find an A, I use the existing S. And now the idea is to just use this type here basically as our preview. So because that's exactly the type we need. So instead of S to maybe A, I change this here to S to either T A. And now I don't need this P prime anymore. And I can just use the P there. And now everything works. And it's even nicer than before. I mean, the implementation is much simpler. And we still have, I mean, because all our prisms we wanted to, I mean, now this all won't work anymore because now the signature is wrong. But we can just recover this old version. So maybe A. So if we just use the Prism prime as before, and now I can just preview review. So I use this more general Prism. Now I must change the preview. I can leave the review and so P prime S case PS of nothing S left S and just A, right A. So that's the definition here from this, sorry, from the slide. This is now basically what I do to get from this signature to this more from this signature to this signature. That's exactly this definition that I now use here. And now, in principle, we could use this Prism prime, except where we actually don't have, I mean, for example, here, where we just have a Prism prime. So now we can use this simplified constructor where we actually do have a Prism prime, I mean. Okay, and now for the other cases where I have an actual prism not primed with 4 parameters, there I still need to like do something. So because the preview is now a different type, so it's now either result, sorry, yeah, either result B or A. So in this case, it's a right A. And in the error case, I now need to keep the error message, and it's a left error E. And now I have to do the same. So here it's fine. Here I have to do the same, so it's not it anymore. So now I must go from maybe A to either maybe B, A. Okay, so if it's just A, I have my A, so it's a right A, and if it's nothing, it's left nothing. And here, so now it's not to this, it's to either maybe B unit. So if it was a just, I go to left. Maybe this is wrong. Yeah, this is wrong. I can't implement this. So there it's really just a maybe prime. And then I can keep the it as before and use this. Sorry. Still need the I need what I had before, but I forgot what I had before. Just sorry. So this is wrong. I think I can't have this. I just have a Prism prime, but now this should work again. Okay, and here this wasn't so difficult last time I gave this lecture. I think there I kept it at Prism primes, but I mean that's wrong, of course. So let's see. And this is now too complicated for me. So I do P, write down the types. On A, B, A prime. So P, what do we have? So we have an either A, B, and we must go to either either A prime B or A. So if it's a left A, we found our A and we return a right A. And if it's a right B, we didn't find our A, so it's a left right B. Okay, and here's exactly the same way. Just the other way around. Almost done. I think I earlier cheated. I mean, in previous lectures. B prime. Didn't do this because I can't remember struggling so much. Okay. So now I need to go from either a B to either, if I don't find the B, the new type, a B prime, or to B. It's a left A. I haven't found my B, so it's a left A. If I have found my B, it's a right B. Oh, this is probably also wrong. Same as for maybe. So I keep this. And cons, I must do something. So this is now from list to either list of the new type, or I find this. So if it's not a cons, then it's a left empty list. Otherwise, it's a right this. Okay. And finally here, actually this it is of course stupid. That should be, we can delete that anyway, because that's an ISO now, obviously. So ISO it. Right. I think everything should hopefully compile again. Yeah. Okay, yeah. So in principle nothing has changed. It's much more powerful only because now we can also change types. So now we can spend the last 5 minutes changing some types. But as I said, everything in principle and the implementations are almost exactly the same as before. So let's see if we take this example again. This example, not that example. Didn't I have an example? This one. Let me just, okay, fine. So for example, now we could change types. I don't know. For example, we could replace the strings by their lengths. So we can do over. Okay, so second component, each element of the list, the justs, the rights, and then length to change a string to an int. Example. So probably so this is, did I change the, I'm also using the just, maybe the justice. The just I have changed. Or the 1 and the 2. I think the 1 and 2 are still missing. Oh, no. I changed those as well, right? Yes, they are correct.
Each over.
Each should also be fine. Each is fine. So it must be the just or the right. Did I reload actually? Yes, I did, I think. Let me just try the just and the right in isolation. So for example, over just length, just Haskell. Okay. So why doesn't it work? Let me try some other, for example, 1. Haskell, comma, true. Probably it's the over. Yeah. Sorry. Probably the over that I didn't change. I did change the preview. I did change the.
Yeah,
No, I
like
didn't change the.
the over shouldn't be a I mean the last.
Yes.
Yeah.
Yes. So I didn't. I just wanted to go through. So I did change the preview. I didn't change the to list off. So that must be a. T. This must be a T. Okay. The view I did change. The set I did not change. T. Okay, the over is wrong, and the over I didn't change, crucially. So B, T, A to B, S to T.
This set has an issue there.
Yes. Set has an issue. But the over seems to be fine now. Must be a B. I set to a B. Okay. So now hopefully everything, I fix everything. So let's first try the simple example. Yeah, I think that's fine. I don't know why this. I think that's.
Because of the number, the length.
Yeah, I think so. No, because I had overloaded strings, hopefully. Instead. So let's see. Over one length. Haskell, not true. Yes, okay. I think that was because of the overloaded strings. Not sure, but yeah, I think so. That error. Okay, so now my earlier example, what was it with this? So here, there was the example here. So I wanted to replace each string by its length. So that would be over. So I go into the second component, each element of the list, only the justs, only the writes, length sample. Yes. Okay, so that worked. So now I can, and the type, of course, is different now. If I ask for the type, I mean, before it was pair of bool, maybe either bool string. Now it's pair of bool, maybe either bool int, because I now changed the strings to ints. So I think that also works. I'm not sure whether I had any cool examples here still. Time is anyway up, but right, I mean, this is also cool. So if I have set both each, I have a list, I mean, a pair of, let's say, list of ints. Pair of lists of ints, 1, 2, 3, 10, 17. I think it's the other way around. To what I want to set is last. Yes. So I started with a list of, sorry, a pair of list of int, and I set in both components each element to an X, so to a character. So I end up with a pair of two strings. And what was the final example there? Okay, that's similar to, so I have something like this. Yeah, okay. So over, what was it? Each swapped prime left length and the list of right Nairobi left true right X. I think this is now because the swapped is not. I think those should be right. So if I change the b comma a to b prime comma a prime, then I end up with a prime comma b prime. And same here. If I change the either ba to an either b prime a prime, then I in the end get an either a prime b prime.
And you have to remove the prime in the ISO constructor.
Yes.
Yeah.
Yes. Right. I think now this example should also work. Yes. So I go to each element in the list, then I swap left and right, and then I go into the lefts, which used to be the rights, and set everything to, no, I compute the length. So now, yeah, it's right 7 because now we are 7 and right 1. And the final example, what was that? Okay, but I think you haven't seen zip yet. So zip, almost done. Zip takes two lists and zips them together. So if I have, for example, zip Haskell and one, the list starting at 1, then it pairs each element of the one list with elements of the other list until one of, I mean, this second list is infinite, but it stops once Haskell is over. So it pairs them like this. So that's a very useful function, zip. And now we can do stuff like over, reversed, zip, Haskell, Nairobi. Why? I think the reversed, I also didn't do this right. Right. If I change the list of A's to a list of B's, then I end up with a list of B's. Okay, and I suppose I could also do this here, right? I mean, it's not, so if I change this to a function from A prime to B prime to C prime, then I end up with a function from A prime comma B prime, C prime. And flipped, if I change this to a function from B prime to A prime to C prime, end up with something from A prime to B prime to C prime. Right, I think now I have removed the primes everywhere where it makes sense. Yes, and now this example also works with this reverse. So, because now I also change the type of the list. I start with a string, so a list of characters, and I end up with a list of pairs of ints and characters. So I reverse Nairobi to Aibo Rian, then zip it with 1 to 7, and then go back and reverse it again. So I end up with this, where it's now like the numbers the other way around. Yes, so that was basically the final example. And that's all we want to do in this course about optics. And I know it's with this profunctors and everything is a bit abstract and probably overwhelming at the beginning. But I mean, one thing I want you to take away is this thing that you don't need to understand everything. I mean, intuitively, you don't have to understand what a choice profunctor is. I mean, sometimes it's enough to just know what the definition is and then just let the types guide you. So often there's just no other way to do, and the compiler can also help very much because it gives you the type of the holes and so on. And often one is in these situations that you have to implement something that's very abstract, you don't really understand it, but it's so polymorphic that you only have a handful of options, and then very often there's basically no choice what to do. So that's the one lesson. And then secondly, you can use lenses without understanding how they're implemented. It's sometimes a bit helpful because you get very strange error messages if something is wrong. But if not, as long as nothing is wrong, I mean, you can just use them without understanding how the magic works. And finally, I mean, there is this, I mean, the most famous lens library is called Lens. It's by Edward Kmet, who is like the most prolific author of hexagonal packages, I think. So that guy is really driven. And there is this insane, I mean, this diagram with, I mean, he has more than we did. So, I mean, we had ISOs and lenses, prisms, traversals, but as you see here, also has folds, setters, getters, and stuff. So there's more in this zoo of optics than we did, but I think those are the most common ones. And he also has like examples here somewhere. I think if you just go, oh yeah, here are examples. But then I also should maybe mention that there are like alternatives. So this is called the Van Laarhoven style of doing optics with these functions of this shape AFA-SFS basically. And then doing like the different ones and getting the subtyping via these constraints, applicative functor, profunctor choice, and so on, which is a clever way to make them composable and also like allow composing optics of different types. However, it also has disadvantages. For example, that you get crazy error messages if you do something wrong. And there are alternatives. So for example, there's one called optics. And that is more like what we did naively. And it's also very nice. And incidentally, it's done by the company of the person that basically created the original slides for this course. So yes, and I mean, you also get all these things, but some of the error messages are nicer. And it's, so yeah, also lots of different types, but we see our our old friends ISO, Prism, Lens, and Traversal, but there are also like lots of others. But this uses a different implementation, which is more like the naive one. But you can nevertheless still compose everything with each other, as in this diagram. And then finally, there's also something called profunctor lenses. So there's yet another way to implement it or to represent these things using profunctors. I mean, we also use profunctors for the prisms and so on, but basically there the lens is a profunctor. And yeah, so I mean, this is not the only way, it's just the most commonly used way. But in practice, to use lenses, it's basically always like the same. And also these optics, for example, they are like compatible with the lens library. So, I mean, the names are very similar and you can use like, I think you can basically turn a lens from the lens library into a lens from the optics library and so on. And all of them have support for like automatically generating stuff. And I should probably show that, at some point, but we will probably have a lecture on so-called template Haskell towards the end of the Haskell part. And maybe then I can show this because that's nice. Then in principle, all you do is, let me see, I'm sure Edward Kmet writes about this. Lens package. Let me see, there's sure there's something called TH. Right. So yes, I don't want to go into this too now, but I mean, if you have a type like this, just as an example, with two constructors, one is a record type with two fields, the other one is a record type with one field, then one just writes this weird thing that you can't understand right now. So that's so-called template Haskell. And then you get all the lenses. So you get a lens foobar to int, which zooms on the X, and you get a traversal Y that zooms on the Y. And there's also, I think, a version for prisms. Make fields. Yeah, make prisms. So it's also possible to get prisms automatically. So in this example, you get automatic prisms foo, bar, and bus from this type. And lots of variations on these things. Yes, so you don't have to implement these things by hand. And this lens library, I mean, there are hundreds of lenses defined or optics defined, but it's quite, I mean, people basically, I mean, some love it and use it all the time, and others think it's incomprehensible because there's so much stuff. So, yeah. But certainly good to have heard of it. Anyway, I think I talked too much, so we should stop now. Are there any questions?
Nope. I think that they need a day to process it a bit.
Yes, sure. But I really encourage you to play with it. I think it's a lot of fun. When I first heard about that, I was absolutely fascinated that that's possible. And I think it's really cool. And it's also useful, I mean, in practice in your own programs. So, I mean, I also had this add example, this add lens to basically go into a map. And that's also very useful. And often you have like some type of state, for example, if you work with a state monad or and that's often a record type, and then there are maps in there and all sorts of things. And using the lens library or something similar, it's much easier to work with it. Maybe as a last remark, I should say that there are also versions that work with the state monad. So once you have, for example, I mean, Zeta, you can think of like a lens. Then there are also things that work in, for example, the state monad. Do we have an example? Yeah, monad state. I mean, we talk about that in the next lecture, but you can just think M is the state monad, for example. And then you have operations where basically you apply a lens to a field in your state directly. And then you can basically, I mean, if you have like a record type, your state type is a record, then you can basically directly in the state monad set, for example, the field of that state to a specific value or so on with these operators. That's also something people disagree about. I mean, there are hundreds of these operators that he defines in this library. So, I mean, you can use them, but I mean, yeah, then you have to learn all of them. But normally there are also like words alternative. And yeah, so a lot is possible, and often it, especially if you have complicated types, it makes it much clearer and easier. Okay, but I think I should really stop here now. And then I think the next topic is monad transformers.
Yep.
On Monday.
Yeah.
So that's also a very nice lecture, I think, and a very important one, but different now to optics. So this was the last about optics.
Yep. And remember everyone to do the homework. Just throwing it out there.
Right. Okay, then yes, talk to you on Thursday. And yeah, Talk to you then. Thank you very much.
Thank you.